Okay, today's topic is analyzing graphs of functions. We want you to be able to learn how to use the vertical line test to test for functions, to be able to find the zeros of a function, and to be able to determine intervals on which the functions are increasing or decreasing, and determine any relative maximum or minimum values of the functions. We'll also help you learn how to determine the average rate of change for a function and identify whether a function is either even or odd. Again, most of this should be review, most of it from either Algebra 1 or Algebra 2. So in the last section, we studied the algebraic form of functions. In this section, we'll study the graphical form of functions. We want you to realize that the graph of a function, any function, we're going to name this function f, is the collection of ordered pairs, and that's usually called x comma y, or it can also be called x comma f of x, which is the value, the output of the function f at a particular value of x, such that x is in the domain of f. Function name is f, okay? So if we're looking at this on a graph, here's what it looks like. We've got our function f here, and we've got our various x values, and we've got our various f of x values. And so any point on this function has an x value and an f of x value, and that is the point x comma f of x. So, because we have inputs and we have outputs, we need to have a name for what all of those together are. So, our domain is our set of all the inputs to a function that each have a single output. Okay? So, if I can have an input that I put into a function and I only get one output out of it, then that number is part of my domain. Okay? So what this means is because each input has only one output, each x is only going to have one y value. Therefore, we can have no two points that lie directly atop each other. So if we're looking at a graph, this would never happen. Bad, bad, bad. So this creates what we call a vertical line test for functions. So if I can have something where 2 points lie on the same x value, and have two different y values, that is not a function, right? So here we have on the second graph, we can look here and see that we do not have that situation. So yes, this is a function. And we say y is a function of x. And on the third one, we have again that same situation. We do not have 2 points that lie directly on top each other like we did over here on the left. So we can say, yes, y is a function of x here. Zeros of a function. Zeros are x values for which the y values, or the output of the function, is 0. So this happens, again, looking at these same three graphs. On this first one, anytime it crosses the x-axis, we have a 0. Why? Because our y value here, our f of x value, is 0 here, right? For that particular input, we have an output of 0. So looking at this other graph here, we had several repeating zeros here, okay? And on this one, we only had 1 0. Okay, so even though this is not a function, it still had a 0, okay? But the other ones were functions, and yes, they had zeros as well. So, finding the zeros of a function algebraically. The only thing we need to do is set our f of x, or our y, equal to 0, and then solve. So, we would have 0 equals x squared minus x. Now, solving for this is where some of your factoring skills come into play. So, I can take an x out of each one of these terms, and I'm left with an x minus 1. Now I can set each factor equal to that 0 and solve. So I have two zeros. I have x equals 0 and x equals 1. These are the points 0, 0 and the point 1, 0. Okay? So if we're looking at a graph of this function, we would know that these are two of the points on that function, and they would both be on the x-axis. Here's another example. Again, set that f of x equal to 0 and solve. In this case, I would want to square both sides, so I get 25 minus x squared, and 0 squared is just 0. I'm going to add an x squared to both sides to get it x by itself, and I get x squared equals 25. Square root both sides, so I get x equals plus or minus 5. So I have two zeros here as well. I have 5 comma 0, and I have the point negative 5, 0. Now, these definitions that I'm giving you on increasing and decreasing functions, I want you to compare them with what we've got in the text, because these are the literal translation of the algebraic form of the definitions that are in the text, okay? And I want you to compare them very closely, because in case you can't understand the algebraic definitions on page 57, I want you to know that these translate word for word. So a function is increasing on an interval if, for each increasing x value, the y value also increases. So as x increases, or moves to the left, y should also be increasing. So if I look at this first function here, it's increasing from the bottom of this valley to the top of that hill, right? On this other function here, it is increasing from this v point, that vertex, on to infinity, okay? Now, a function is decreasing if on an interval if, for each increasing x value, or as x moves to the right, the y value decreases, sorry. So if we're moving x to the right, y should be decreasing or going down, okay? And on this graph here, it happens from the top of the hill to the bottom of the valley. On this graph here, it happens from negative infinity here to negative 1 for x. So we always give our increasing or decreasing in terms of x. So for this, we would say the function is decreasing from negative infinity to negative 1, and it increases from negative 1 to positive infinity. At negative 1, it's important to note that it is neither increasing nor decreasing, nor is it constant, because determining that something is constant also means that you have to increase the x value, and we only have one x value here. So a function is constant on an interval if, for each increasing x value, the y value is constant. So we have to have at least 2 points where we have the x being the x value changing and the y value staying constant, to have an interval where the function is constant. I hope that makes sense. If not, replay the slide and write down some questions. Now let's talk about relative minimums and maximums. These are defined for you on page 58, and this is again a translation so that in case you don't understand the symbols used in the definition, we can talk about it in real English terms. So a function value is called a relative minimum if, over a specified interval, it has the lowest value, the lowest y value, okay? I should add that as a y value. Okay, so what this means is if you're looking over that interval, some interval of x inputs, right? And you're looking at, and you're seeing at one point, we've got the lowest y value happening of any other y values on that interval, then that is called a relative minimum. Conversely, if it has the highest y value, we call that a relative maximum. So let's draw this out and see what this looks like. So I've got, let's do that little curve thing here. So if I'm looking at this interval from here to here, right? So I'm going to annotate that from here to here. And I'm looking and saying, what is my relative minimum? Well, my relative minimum is here, and my relative maximum is at the top of the hill, okay? Now, we know that this function in actuality keeps going and but we're only looking at this specific interval, okay, of x values. Average rate of change. We know that slope is a rate of change. Now, for each nonlinear, which means curvy graph, whose slope changes at each point, okay, so let's break that down and see what that's talking about. So we have a curvy graph where the slope changes at each point. So we're looking at something maybe like a parabola, okay, where my slope is different at each point, right? The average rate of change between any 2 points, and we're going to call those points x1 f of x1 and x2 f of x2, is just the slope of the line between the 2 points. Okay, so we find 2 points, we calculate the slope between them, and that's the average rate of change for the function. Very easy. Same skills that you've been doing since Algebra 1, we're just applying them slightly differently. So if I've got x1 is 1, then f of 1 is -3 times 1 squared plus 1, which is just going to be -2. So that gives me the point 1, -2. And f of x2 is f of 3, so -3 times 3 squared plus 1. 3 squared is 9, times -3 is -27, plus 1 is -26. That gives me the point 3, -26. If I want to find the average rate of change for the function on that interval, then I will just find the slope of that. So average rate of change will equal the slope, which is -26 minus my -2 over 3 minus 1. So this is -24 over 2, which is -12. So over that interval, the average rate of change is -12. So for each increase of 1 unit, we go down 12 units on average. Let's now talk about even and odd functions. Even and odd functions are just another way of saying what things are symmetrical with, okay? So even functions are always symmetric with the y-axis. Odd functions are always symmetric with the origin. There is no real term for things that are symmetric with the x-axis. Now, test for even functions. We've done this before. We did this in the last lesson, but we didn't quite say, yes, this is what it is for even functions. So we know that for even functions, the value of my function at a negative value of x should equal the same value of my function at that positive value of x. Why? It's symmetric with the x-axis, right? So if I've got a positive x over here, at negative x, I should have the same point because it's reflected across that axis. So I want to test to see if that's the case. So I'll evaluate my function at negative x, evaluate my function at positive x, and see if they're equal. Now you can do this with actual real numbers, but sometimes that results in errors, but it's a good check. You can also just plug in negative x into your function and see if you get the same thing as your original function, okay? Now let's talk about the test for odd functions. F of negative x equals the negative of f of x, okay? We know that they're symmetric about the origin, okay? So if I've got x and I've got negative x here, then f of negative x, say it's down here, should be the negative, and the negative of a negative in this case would be a positive, of f of x, okay? So they should be 180 degrees different from each other. So we're going to evaluate the function at f of negative x, evaluate it at negative f of x, and see if they equal each other. Now, one hint on even versus odd functions. For polynomial functions, even and odd refers to the highest degree polynomial. So if you've got an x to the 5th type polynomial, you're going to test it to be an odd function. You're not going to test it to see if it's an even function. If you've got an x squared function, you're going to test it to see if it's even, because 2 is even and not odd. Okay, so that should help you narrow down which tests to do. Now that applies for polynomial functions, but not all polynomial, not all functions, I should say. So let's test an example. This first one, we have 2x squared plus 1. We would test that for even because this 2 is even. Okay, so for even functions, we know that f of negative x should equal f of x. Now f of x is this right here. So let's see what f of negative x is. So 2 times negative x squared plus 1. Well, negative x times negative x is just positive x squared. So we know that f of negative x does equal f of x because these two are the same thing, so this function is even. Okay? That means it's symmetric with respect to the y-axis. Now, this next function, we've got 5x cubed plus 4. Because 3 is odd, we would test this to see if it's odd. Now, the test for odd is f of negative x should equal the negative of f of x. So let's find out what f of negative x will equal. And that is 5 times negative x cubed plus 4. Well, negative x times negative x is positive x squared, times another negative x is negative. So I should have negative 5x cubed plus 4. And then we know that we need to test for negative f of x. Well, that's going to be the negative of 5x cubed plus 4. That's like saying I have a little negative 1 here that I've got to distribute to everything. So that will end up being negative 5x cubed minus 4. Now, at this point, we are seeing, does this equal that? Well, we can see that it doesn't because of the negatives, okay? So this is not odd. And we know that this makes sense because if I have 5x cubed plus 4, what I'm taking is I'm taking the 5x cubed and I'm raising it up 4, right? So say that this is 4. Is this function symmetric with respect to the origin? Well, it can't be. It doesn't go through the origin anymore. So we could have actually, knowing how these functions work, looked at that and said, hey, no, it's not going to be odd. I can look at that function and see that it's not going to be symmetric with respect to the origin. So what we've learned to use the vertical line test for functions. We've learned to find the zeros of a function. We've learned to determine intervals on which functions are increasing or decreasing, and how to determine relative maximum and minimum values for functions. We also talked about average rate of change over an interval for a function, and we learned how to visually and algebraically identify even and odd functions.